Hello, I'm Ryan Downey, Principal Engineer for AVO Training Institute's Electrical Engineering Division. And for this presentation, I'll be discussing harmonics in electrical power distribution systems. The discussion will include in detail the IEEE standard that explains and provides recommendations and requirements for harmonic control. Also included in the discussion will be the various types of harmonic sources and the cause-effect problems they can create and how they can possibly be mitigated. Please feel free to send me any questions you may have during the presentation. I may or may not have time to answer the questions as we go, but all questions will be followed up via email. Here's a little information about me. I have over 10 years of experience in electrical engineering. I'm currently licensed in 40 states across the U.S. I'm also licensed in Puerto Rico and Alberta, Canada. I'm an active member of IEEE 1584, which is a standard of IEEE that provides a method of calculating the incident energy of arc flash events. I am also an active member of IEEE 1814, which will be a standard of IEEE that will provide recommendations for implementing various types of electrical safety standards, techniques into new design projects to improve electrical safety. So for our learning objectives, we will discuss the following. What exactly are power system harmonics? What causes harmonics? What are the effects of harmonics? What standards or guidelines are available to help control harmonics? And how can we mitigate harmonics? So just an overview on harmonics. The power quality of electrical distribution systems has a drastic effect on power regulation and consumption. Power quality includes all aspects of events in the power system that deviates from normal operation, which includes harmonics. This is especially true nowadays with the computer age we live in, and there are all sorts of electronic power sources that can cause distortion and waveforms of the power system. Harmonics or distortion on a power system caused by nonlinear type loads such as variable frequency drives, or commonly referred to as VFDs, large computer systems, SCADA systems, electronic lighting ballasts. These types of loads are accounting for a significant portion of the total load for various types of facilities. IEEE Standard 519, which we'll discuss a little later, sets the requirements for harmonics and creates limits for harmonic distortion. I'll also discuss different ways that harmonic distortion can be mitigated. So what exactly are harmonics? Well, essentially harmonics are a mathematical way of describing distortion to a voltage or current waveform. And you can see here we have a calculus problem, which is a Fourier series equation I'm sure everyone is dying to solve. However, understanding the math is not important. It's important to understand that harmonics are a steady state phenomenon and repeats with every cycle. Harmonics should not be confused with transient dips, spikes, impulses, oscillations, or things of this nature. Also, the term harmonic refers to a component of a waveform that occurs at an integer multiple of the fundamental frequency. Harmonic distortion is the degree to which a waveform deviates from its pure sinusoidal values as a result of the summation of all the harmonic elements. So for a 60 Hertz fundamental frequency waveform, the second, third, fourth, and fifth harmonic components will be a 120 Hertz, 180 Hertz, 240 Hertz, and 300 Hertz respectively. Also, an ideal sine wave should have 0 harmonic components. And here you can see what I mean by an ideal waveform having 0 harmonic components. The waveform on the left does not have any harmonic components and is essentially a pure waveform with linear loads. Linear loads draw current that is sinusoidal in nature, so they generally do not distort the waveform. Nonlinear loads, however, can draw current that is not perfectly sinusoidal, as shown in the figure on the right. Since the current waveform deviates from a sinusoidal wave, voltage waveform distortions are created. As you can see, waveform distortions can drastically alter the shape of the sinusoidal waveform. However, no matter the level of complexity of the fundamental waveform, it's actually just a composite of multiple waveforms called harmonics. Here we have waveforms that show how the harmonic components combine to form a resultant waveform with much distortion. The graph on the left shows the fundamental frequency waveform combined with that of the fifth harmonic and seventh harmonic waveforms to form the graph on the right. And here we have a nonlinear waveform that shows clipping. This type of waveform is common in electronic devices having nonlinear characteristics such as computer-based equipment. When the sine waves are distorted symmetrically about their average values, then they're composed of odd harmonics only. Power is supplied by a three-phase system where each phase is 120 degrees apart. This is done for two reasons. First, it is because motors and/or generators that use three-phase power are more efficient due to the constant torque the phases supply. Second, it is because after power supplied to the load, the three-phase can theoretically be added onto the neutral wire and cancels each other out. This saves the utility company from creating return wiring to the power plant. However, if the three phases contain third-order harmonics, the currents will not fully add to zero or cancel out. As you can see in the graph, the third harmonics between the phases add together, which creates oscillating current. This results in a sharp increase in the zero sequence current, which increases the current in the neutral conductor. This effect can require special consideration in the design of an electric system to serve nonlinear loads. To avoid third harmonics adding together, delta connections are used and the current is cycled around the connection instead of a Y connection. Most harmonic problems are caused by the third harmonic. For the most part, harmonics were absent until the 1960s with the coming of age in computer systems and electronics. With the beginning of this area, harmonics began to surface. As I mentioned, harmonics are caused by nonlinear type loads. Power sources act as nonlinear loads and draw a distorted waveform that contains harmonics. 75% of all electrical devices in North America operate with nonlinear current draw. So here we have a list of devices or components that can cause issues with harmonics. As I mentioned, variable frequency drives or VFDs, universal power supply systems, commonly referred to as UPS systems, DC converters, solid state rectifiers, arc welders, heater units or furnaces, switch mode power supplies such as those used on computers, electronic lighting ballasts, PLC systems, SCADA systems, computer systems. All of these are sources of harmonics. So let's talk about the effects of harmonics. Harmonics can have detrimental effects on electrical equipment and power systems. Unwanted distortion can increase the current in power systems, which results in higher temperatures in neutral conductors and distribution transformers. Harmonics can also cause the overheating of transformers, motors, generators, capacitors, cables or conductors, etc., which can result in premature failure. Harmonics can also cause misoperation of circuit breakers and other types of protective devices, as well as malfunction of electronic equipment. Harmonics can also result in incorrect readings on meters, which can cause a whole set of other problems and can also cause malfunction in instruments, including medical instruments, which can obviously have serious consequences. Going on with the effects of harmonics, harmonics can also result in premature failure of power supplies due to distortion of the supply voltage. Harmonics can also result in a low power factor, requiring a transformer to be upsized in kVA or neutral upsizing. Harmonics can also cause resonating and heating of power factor correction capacitors, which can cause failure. The power quality of distribution systems has a drastic effect on power regulation and consumption. Another phenomena that related to harmonics that can occur is system resonance. Resonance occurs when a harmonic frequency produced by a nonlinear load closely coincides with a power system natural frequency. The likelihood of effects from harmonics occurring greatly increases if a resonant condition exists or occurs. The single largest cause of severe harmonic distortion is resonance. A normal harmonic may be amplified 10 to 25 times if resonance occurs at or near critical frequencies. Resonance occurs mainly due to improper use of power factor correction capacitors or because of incorrect application of filters. There's two forms of system resonance: parallel resonance and series resonance, and we'll talk about those. So parallel resonance occurs when the system inductance, reactance, noted here on this drawing as XL, and the capacitance reactance, noted as XC, are equal at some frequency, like the fifth, seventh, etc. Harmonic currents that flow between capacitors and the system inductance are significantly amplified, typically up to 10 to 15 times. Parallel resonance can lead to capacitor fuse blowing or failure and/or transformer overheating. So series resonance is a series combination of inductance and capacitance. It creates a low impedance path for harmonic currents at the natural frequency. This results in high harmonic currents through the capacitors. Series resonance can result in a high voltage distortion level between the inductance and capacitance. So IEEE standard 519 was created to establish limits for harmonic distortion and provide direction on dealing with harmonics. It was intended to provide direction on dealing with harmonics introduced by static power converters and other nonlinear type loads. The standard was written to establish goals for the design of electrical systems with both linear and nonlinear loads. It is presented as a guideline for power system design when nonlinear loads are present and assumes steady state operation. Distortion limits for both current and voltage are defined in order to minimize interference between the electrical equipment. The limits are defined at the point of common coupling, which I will discuss. The standard is titled Recommended Practice and Requirements for Harmonic Control in Electric Power Systems, and the current standard was released in 2014. So the point of common coupling, it's defined as the point in the power system closest to the user where the system owner or operator could offer service to another user. Frequently for service to industrial users, for example, manufacturing plants, via dedicated service transformer, the point of common coupling is at the high voltage side of the transformer. For commercial users that are supplied through a common service transformers, the point of common coupling is typically at the low voltage side of the transformer. The point of common coupling is basically recognized as the point where any harmonics can migrate onto the utility system and cause problems for other customers. So here we have a couple of diagrams of the location of the point of common coupling, and you'll notice how it's basically the point of common coupling is basically the point at which another customer could be served. So you can see the different types of scenarios we have. So more on the point of common coupling, the intention of having the point of common coupling is to prevent a high level of harmonics, such as that generated by nonlinear loads, generated by one customer from causing distortion at another customer on the power grid. In considering the primary side of a transformer that supplies only one customer, the transformer's impedance will decrease the short circuit ratio. This results in an increase in the harmonic current limits. The voltage distortion will be higher at the secondary of the transformer. So going over some of the definitions we have in IEEE 519 standard, the short circuit ratio is the ratio of the short circuit current available at the point of common coupling to the maximum fundamental load current. This ratio essentially shows the relative size of the load compared to the utility system. The maximum load current is recommended to be the average current of the maximum demand for the preceding 12 months. Unfortunately, this value is inherently ambiguous, making it difficult to derive at the design stage when measured load is not available. So looking at this graph, this shows a high short circuit current, and which results in minimum voltage distortion. And let me switch over to this next slide, and you can compare. And on this graph, you can see the low short circuit current, which results in a significant voltage distortion. The distortion is much more pronounced, as we saw, than the one on the previous graph. So here you can see the larger loads have a greater ability to cause voltage distortion on the utility system. And now let's discuss more mathematics. Here we have the equations for total harmonic distortion and total demand distortion. These equations can be used to describe voltage or current distortion. The total demand distortion equals the total harmonic distortion multiplied by the ratio of nonlinear load to the total demand load, which includes both linear and nonlinear loads. Per the IEEE 519 standard, these equations consider components up to the 50th order. However, I'd like to note, it also notes that components of order greater than 50 may be considered if necessary. More definitions here. The voltage total harmonic distortion of the waveform is the ratio of the root sum square value of the harmonic content of the voltage to the root mean square value of the fundamental voltage. Similarly, the current total harmonic distortion of the waveform is also the ratio of the root sum square value of the harmonic content of the current to the root mean square value of the fundamental current. So these formulas show the total harmonic distortion on a signal. The end result is a percentage comparing the harmonic components to the fundamental component of the signal. The higher the percentage, the more distortion that is present on the signal. We'll discuss harmonic limits. Since managing harmonics in a power system is considered a joint responsibility involving both the supplier and the end users, IEEE 519 places recommended harmonic limits for both voltage and current. The recommended values are based on the fact that some level of voltage distortion is generally acceptable, and both parties must work together to keep actual values within acceptable levels. By limiting the harmonic currents by users, the voltage distortion can be kept within acceptable levels. IEEE 519 also states that the recommended limits only apply at the point of common coupling and are not to be applied to individual pieces of equipment or at location within a user's facility. In most instances, the harmonic voltages and currents at these locations can be found to be significantly greater than the limits at the point of common coupling due to the lack of cancellation or other phenomena that tend to reduce the combined effects of multiple harmonics sources. So this is table 1 that's in IEEE standard 519/2014, as we can see here. That establishes the harmonic limits on voltages as 8% for total harmonic distortion, and 5% of the fundamental voltage for any single harmonic. This is for system levels up to 1,000 volts. And on this table, you can see the limits for system levels between 1,000 volts and up to 69,000 volts have harmonic limits on voltage as 5% for total harmonic distortion and 3% of the fundamental voltage for any individual harmonic. You'll also notice it shows limits for voltage levels up to 161,000 volts. It should be noted that even if the voltage distortion limits are met at the point of common coupling, they could very easily be exceeded downstream where connected equipment could be affected. Since voltage distortion is a result of harmonic currents passing through the impedance of the power system, voltage distortion is always higher downstream where the harmonic currents are generated and where system impedance is the highest. Now let's look at the current harmonic distortion limits. For power systems with voltage levels between 120 volts and 69,000 volts, the limits can be found in Table 2 of the standard, which is shown here. I would also like to note that Tables 3 and 4, which are not shown here, show the current distortion limits for higher system voltages. The table defines total demand distortion current limits as well as individual harmonic current limits. The limits are most severe for short circuit ratios of less than 20 because this lower ratio indicates a high impedance power system or a large customer or both. Voltage distortion is more likely to develop from current harmonics consumed at a point of common coupling where the short circuit ratio is low, thereby justifying the more severe limits. So discussing further the current harmonic distortion, is recommended that the limits be increased by a multiplying factor when actions are taken by the user to reduce low order harmonics. And as we can see in this is Table 5, the multipliers in the second column are to be used when steps have been taken to reduce the harmonic order shown in the first column. Please note, however, that the low order harmonic currents must be kept below 25% of the current harmonic distortion values shown in Table 2. So power factor must include the distortion factor to account for harmonics. Here we can see how the distortion factor is determined. The distortion factor decreases as harmonics increases. True power factor may be lower when the effects of harmonics are considered. So here we have a couple of graphs. The graphic on the left shows a typical power factor diagram, and the graph on the right shows a power factor diagram with harmonics included. You'll notice how the harmonics are factored into the equations as well. Real power is useful work-producing power. Reactive power is unuseful, non-work producing power. As an example, imagine you have a full glass of beer. The foam at the top is not very useful, just as reactive power. However, the beer below that is very useful, just as real power. So the classic example of a nonlinear load is a rectifier with a capacitor input filter, where the rectifier diode only shows, or excuse me, only allows current to pass to the load during the time that applied voltage exceeds the voltage stored in the capacitor, which might be a relatively small portion of the incoming voltage cycle. The characteristic current harmonics produced are determined by the pulse number, and here you can kind of see the equation. So here's an example of a 6-pulse rectifier with harmonics present. You'll notice how the 5th, 7th, 11th, 13th, 17th, 19th, and so on, harmonics are present. The current is quite distorted, and the typical full load current harmonic distortion at the transformer primary can be anywhere but from 25% up to 48%, depending on the network impedance, even with a 3% reactor. And here we have an example of a 12-pulse rectifier with harmonics present. You'll notice that the 5th and 7th harmonics are not present, as we saw on the 6-pulse rectifier. The typical full load current harmonic distortion at the transformer primary is between 8% and 12%. And here we have an example of an 18-pulse rectifier. You'll notice that the 11th and 13th harmonics are not present, as we saw on the 12-pulse rectifier. The typical full load current harmonic distortion at the transformer primary is between 4% and 6%. This graph shows the effect of increasing the AC input percent impedance on the input current harmonics. The 6-pulse rectifier cannot reduce the input current total harmonic distortion below 25%, even with an input AC reactor with 10% impedance. And you can see that the 12-pulse and 18-pulse rectifiers can achieve an input current total harmonic distortion of less than 10% with the addition of an input AC reactor of 1 to 2% impedance. So as we've seen, 12 pulse, or better yet, 18 pulse drives are preferred over 6 pulse drives due to the reduction of harmonics. As a rule of thumb, the magnitudes of the harmonic currents will be the fundamental current divided by the harmonic number. For example, the magnitude of the 5th harmonic would be 1/5 of the fundamental current. VFDs also produce harmonic currents at the output of the inverter, which are seen by the motor. So let's talk about harmonic mitigation. With the increasing demand of nonlinear type of equipment and loads, mitigation of harmonics becomes more and more important. If harmonic study or testing indicates excessive harmonic levels or a potentially harmful resonance condition, mitigation must be considered. Depending on the specific situation, there are often several different methods to look into for mitigating the harmonics. So what are some of the methods we can utilize to mitigate the harmonics? Well, of course, we could limit the amount of nonlinear loads, but this is typically not an option with the necessity of these loads with limited resources. Line reactors and motor drive isolation transformers use reactive harmonic attenuation effects to reduce the actual current distortion at the input terminals to the drives. Line reactors are more commonly used because of their size and cost. As we discussed earlier, we could replace 6-pulse drives with higher pulse drives, such as 12-pulse or 18-pulse drives. Harmonic filters can be used to mitigate problems as well. They're used in applications with a high nonlinear load to overall system ratio to eliminate the harmonic currents. They can be tuned to a specific harmonic, such as the 3rd, 5th, 7th, 11th, etc., to meet the requirements of the IEEE 519 standard. Active filters insert negative harmonics into the network, thereby eliminating the undesirable harmonic on the network. Passive filters are a combination of capacitors, inductors or reactors, and resistors. They're the most common and are available for all voltage levels. Resonance problem indicates removal or relocation of power factor correction capacitors. Overall, it's important to understand how the various system components interact with each other and with the power system. It is essential that a coordinated solution be provided which meets total harmonic distortion levels, system performance demands, and power system requirements. Correcting harmonic distortion problem in the field after installation can be very challenging, time-consuming, and very costly. So now I'll go over a few of the different filter types available for harmonics mitigation. Harmonic filters can be used to mitigate harmonic problems as well. They generally consist of one or more tuned inductor capacitor legs, which shunt specific harmonic currents away from the power system. They also offer the added benefit of supplying leading reactive power and thus provide power factor correction. Here we have an active filter front end with a LCL filter. The active filter line inverter removes low frequencies less than 1 kilohertz. The SCL filter, which you can see all this on the diagram, LCL filter is a passive filter, removes high frequencies greater than 1 kilohertz, the current and voltage. The SCL filter is inserted between the rectifier and the 3-phase power supply. This attenuates the pulse width modulation harmonics so that proper voltage and current total harmonic distortion levels are obtained. For this particular setup, no transformer is required, and performance is actually not affected by line imbalance. A parallel active filter is an option to help mitigate harmonics. It works by sampling the distorted current and uses fast-acting transistors to generate harmonic currents and inject them 180 degrees out of phase. The pros of using these filters are they're sized to harmonic content only. They maintain good performance at light loads. The cons of using these filters are they're expensive, they're susceptible to background voltage, total harmonic distortion, and imbalance. Also, the complexity requires startup and regular service by the manufacturer. Another option to help mitigate harmonics is to use a VFD with an active front end, or also known as an active rectifier. The 6-pulse diode bridge rectifier is replaced by a fully controlled transistor bridge. The pros of using this device are it ideally achieves the lowest current total harmonic distortion. It can provide regenerative braking. The cons of using this device are it is expensive. It can introduce higher order harmonics, and it can result in higher electromagnetic radiation as well. The complexity requires startup and regular service by the manufacturer. So here we have an overview of the effectiveness of different types of harmonics mitigation methods. No mitigation can typically result in a 72% total harmonic current distortion. That's with doing nothing. The percent harmonic reduction is based on the current total harmonic distortion for a given method as compared to no mitigation at all. So looking down the list, you can see how different methods are more effective than others. So harmonics can also be measured or monitored using specific metering equipment. A digital oscilloscope shows the wave shape, total harmonic distortion, and amplitude of each harmonic. True RMS multimeter gives correct readings for distortion-free sine waves and typically reads low when the current waveform is distorted. The instruments used to measure harmonics should comply with the IEEE specifications, which are detailed in IEEE 519/2014 standard. There are requirements for the measurement window and cycles to properly display the spectral components. There are also requirements for measurement of harmonics over daily and weekly observations. So it's important to check the IEEE 519 for these requirements. So harmonics analysis is a mathematical way of simulating or predicting harmonic distortion levels and potential resonances based on the power system data. The electrical distribution system is modeled using proven engineering software, and harmonics analysis performed in conjunction with other power systems analysis, such as short circuit analysis, etc. It is recommended that the analysis be performed by, definitely should be performed by a qualified person, preferably a licensed electrical engineer. Also, mitigation methods can be analyzed to determine the effects of adding different types of equipment to limit or eliminate the harmonics. So when should a power distribution system be monitored or evaluated for harmonics? Well, it is always best to perform an evaluation of harmonics during the design stage. This is very true if large capacitor banks, which are typically used for power factor correction, or other harmonics generating equipment will be used. Also, if capacitor banks will be incorporated into an existing system, a harmonics analysis or evaluation should be considered, especially if 20% or more of the load includes other harmonic generating equipment. It is recommended that a harmonics analysis and power system modeling be performed in the event that large nonlinear loads will be added to a large facility, especially if the new loading comprises 25% or more of the existing load. If the facility has a history of harmonic-related problems, such as brownouts, voltage flicker, capacitor fuses being blown, or some of the other things I previously mentioned, an evaluation should definitely be considered. So in conclusion, harmonics can result in decreasing power system reliability. Understanding the causes, potential effects, and mitigation methods can reduce or eliminate harmonic type problems. Mitigation should be considered if nonlinear loads are a significant portion of the total system load, which we went over. Also, in conclusion, applying the harmonic limits per IEEE 519 can be challenging, and it's important to understand the requirements. Mitigation methods can be determined with a proper harmonics analysis. It is recommended that the harmonics analysis be performed by qualified personnel, and it is essential that a coordinated solution be provided which meets the total harmonic distortion levels, system performance demands, and power system requirements. And that concludes the presentation. Once again, I appreciate your time, and I apologize if I was unable to answer any of the questions. However, I will follow up with an email to each and every questions that were submitted, and thank you.